How's everybody enjoying the snow today? Great, right? We'd like to have snow every day in Connecticut. April, May, June. Too much snow, right? Yeah, I know. Just got to wait a little bit more. We'll have good weather. All right, so last time we finished kind of with this idea here, where we're doing the analysis of quicksort. And Cn was the number of average comparisons. And we set up a model, and we solved the model, and we basically got this result. And then we substituted for natural log of n, we substituted Lg of n by using the change base rule, and we got this important result, 1.38 n log n. And so therefore, since the average number of comparisons, by the way, if I ask you a question on a final exam, yes, I know, final exam, scary sounding, but if I ask you the question, because basically, I know you can memorize this, or I can assume that you can memorize this, but this is, we call this the average analysis, right? Average analysis of the complexity. But average is always dependent upon what? What does average always depend on? Go ahead. Probability, and also it depends on our what? On our assumptions. Okay? Assumption, meaning the average analysis depends on what we think is average. Okay, so my question is, this is the result of the average complexity of quicksort. What are the assumptions? Can somebody tell me the assumptions? And I will start you off. I will help you. The assumptions I'm looking for is specifically one assumption. And this assumption is going to be with respect to the pivot element, or any pivot element under consideration. What is the assumption of our analysis with respect to the pivot element?
First element is the pivot.
Say again?
First element is the pivot.
Well, that's true. So the answer was it's the first element of the array, but that's simply the selection of the pivot. I'm more interested not where the pivot comes from, but where the pivot goes to in terms of probability. So what's our assumption with regard to the pivot? Where does it go? With what probability? To make this the average analysis.
Middle of the...
Well, we hope it's in the middle, but it's not always in the middle. So our analysis doesn't, we don't assume it's going to be in the middle. Because if we assumed it's in the middle, our analysis would be best case analysis. Because that's the best case.
If we assume it is in the last, then it would be the worst case.
I understand that. So therefore, that's the worst case. Middle is the best case. What is our location of the pivot according to this analysis, which is the average case? Scott, you want to say something?
No.
Okay. Anybody else? What is our assumption with respect to the pivot? It's a very simple assumption, but it is our assumption.
It's a sort of place like left to it will be the...
That's the way the algorithm, that's the way partition works, always. But what I'm saying is, our analysis, when I say our analysis, I'm really talking about if we have to go all the way back to the beginning. And we're setting up the analysis right here. So this is now the analysis, right here. What is the basis of calling this C of n average case? What are we saying with respect to the pivot? Yes, but I'm looking for a probability.
1 over n.
Well, kind of, sort of. You're sort of there.
No.
Our assumption for our average case analysis is that the pivot is equally likely to fall anywhere. That's the assumption of our, okay. If that's true, then our analysis is spot on for the average case. Because we are looking at, this is the case where there's no left side, everything's on the right, which means our pivot goes to the leftmost location, because there's nothing to the left. This is the case where the pivot goes where? Where's the pivot going in this partitioning, in this split? Remember, this is Cn, right? Cn is going to split into two pieces, the left and the right. This is the left, this is the right, in one instance. This is the left, this is the right, in another instance. And it continues. This is the left, this is the right, this is the left, it's the right. So in this case, how many elements are on the left of the pivot?
0.
0. How many on the right of the pivot?
N minus 1.
Which means the pivot goes where?
Left.
First location on the left. Now, where does the pivot go in this case?
Second.
Second place on the left, and we have 1 to the left of it, and n minus 2 to the right of it. Where does the pivot go in this case?
Rightmost.
Rightmost location, and that's why n minus 1 are going to be on the left. And because all these possible ways are n ways of doing it, we divide it by n, giving them equal weight, equal probability. We're not saying the pivot is more likely to go in the middle or more likely to go on the outside. We're saying its probability is equally likely, and we do that by simply multiplying each one with a probability of 1 over n times this, plus 1 over n times this, 1 over n, 1 over n, 1 over n, 1 over n. Just divided by n, it's 1 over n, right? That's what I'm talking about. Okay, so that was the assumption I was looking for. Now what we want to do is we want to look at, let's see. Okay, I'm looking for, okay, so here, sorry, I keep messing around here. So this is, where's the result here? So this is the result. So now what we wanted to do is we wanted to also analyze, since we kind of got this part down, we wanted to analyze the average height of a BST, the average height of a BST. And again, you have to think about how do we define an average height? So we're going to define the shape of a tree, not the shape, maybe the height of a tree, by the sum of the depths of all the nodes in the tree. Because if I can define the tree by the sum of the depths of the tree, so for example, if you have a tree that has one root, what's the depth of a root? 0. And what's the depth of two children? 1 each, so it's a 2, 2. And then if you go here, it's going to be, so it's going to be 1, 1 is 2. Then we have 2, 2, 2, 2. It's going to give me 8. But then if we have only 1 here, that's going to be a 3, 4, another 4, 5, another 5, 6. So we're going to add the depths of the tree. If we add the depths of the tree, and we divide them by n, what will that tell me? If I add the depths of all the nodes in a binary tree, and I divide by n, what will that tell me? Are your brains frozen from the snow?
Yes.
Were you guys watching the snow all night? All excited? Okay, go ahead. Ronaldo?
The average depth.
It's going to give me the average depth. The average depth. Now, what do you think is the average depth of a balanced tree? What's the average depth of a balanced tree? Let's think of a balanced tree. Let's make the case for the perfect balanced tree, which is a full tree. So if a tree is full, it just goes, every level is perfectly full, right? What's the average depth? Well, I don't know what the answer to that is, but I do know that the bottom level of a full tree has 50% of the nodes. And its depth is what?
N minus 1.
Its depth is what?
Log n.
Log 2n
Log
minus 1. We can forget about the minus 1. Log 2n. So the height of a full tree is log 2n. And the number of nodes at the bottom level is half. So 50% have a depth of this. So we can actually do a summation of this if we wanted to. We could do a summation as the depth d goes from 0 to log 2n, minus 1 if you like. Okay? And we're going to add what? What's the term going to be? So we're going to go level by level, and we're going to multiply what? The number of nodes times the depth. D, the depth, is going to start at 0, and it will actually go to log n minus 1, and then we'll multiply the number of nodes at the depth times the depth. What's the depth, first of all? What's the first depth we're going to use? 0, and that represents?
No.
That represents the root. 0 is the depth. And how many nodes do we have that are roots?
1.
And how do we, if I is the index 0, and 0 is the depth, how do we represent as a power of 2 one root?
2 power 0.
2 to the 0. So it's going to be 0 times 2 to the 0. When we go to level 1, I is going to be equal to 1, and we're going to have a depth of 1 times 2 to the 1. So it's just going to be the summation of I, 2 to the I, as I goes from 0 to log 2 n minus 1. Now, can we figure that out? Yes, you can figure it out, because we learn in the mathematical tools the summation from 0 to n of I, 2 to the I. And we have a solution for that. Remember that? It's in your notes someplace, it's in your cheat sheet someplace, right? So in order to find out what is the value of 0 to n, or 0 to log 2n minus 1 of I, 2 to the I, all we need to do is go to our result and plug in what? Plug in log 2n minus 1 as a substitution for? As a substitution for n. And once we simplify it, we'll have this result. So that would give us what? That would give us the summation of the depths. Because it's the depth times the number of nodes, depth times the number of nodes, depth times the number of nodes. Add them all together, you get the summation of all the depths times the number of nodes, you get the total depth.
That's substitution for I, right?
Substitution for n, for the upper limit. Because our solution, I think, said we will. First of all, if you go from 0 to n, I to the I, the first term is 0. So it's the same thing as 1 to n, I to the I. Correct? So therefore, what I'm saying is, instead of going from 1 to n, go from 1 and let n be log base 2 of n minus 1. And then substitute to our closed form results, simplify it, and you'll get that. When you take that and you divide it by n, you'll get what?
Average.
The average depth of a node. Which, by the way, let me tell you what it is. The average depth of a node of a full tree, where the bottom level is, for example, the 10th level, is 9. So the average depth is actually 1 less than the deepest level. It's like, so how come it's not in the middle? Because the tree doubles its population, if you will, every single level. So therefore, the bigger numbers, the bigger depths, are much more of the bigger depths than the smaller depths. So it pulls the average down to the worst case. But the worst case is still really, really good, because it's log 2n. Does that make sense? Yes? Okay. So that can tell us the average depth of a node of a full tree, which is very, very close to being the same thing as that of a balanced tree. What's the difference between a tree which is full and a tree which is balanced but not full? Anybody? What's the difference between a tree that's full and a tree that's balanced but not full? Ravia?
Nodes are not complete in the tree. I mean,
Where? In which level?
In imbalance, in lower level.
In the lowest.
Level.
Yeah. So in a balanced tree which is balanced but not full, it means that the lowest level may have some missing nodes, but every other level is full. So the exception is the bottom level, which is not completely full.
That's balanced.
That's balanced. That's balanced. So basically, think of it as a tree, perfect like this, and then we have some missing teeth in the bottom. Wow. All right.
In that case, the average depth of the tree would be also different.
Say again?
In that case, average depth of the tree would be different.
It would be still the same theta. It would still be the same theta. Okay? Because if you think about it, if you have a full tree, and let's say the maximum depth is k. So the average depth will be
K minus 1.
k minus 1. Now take the same tree where the maximum depth is k, but it's not a full tree, but it is balanced. That means this tree will be either, it will be missing nodes on the bottom. There may only be one node at the kth level, or there may be a whole lot of nodes at the kth level. We may be, if it's only one node at the kth level, then we really have, the deepest level is almost k minus 1, which means the average depth would be
K minus 2.
k minus 2. So k minus 2 is still theta of k.
Okay.
Okay, so you get the idea. All right, so we can only be off by 1, so that's why I'm saying it's still the same theta. But the average tree grows uncontrollably. We don't have any belief that it's going to have actually fullness at all, or certainly it's not going to be balanced. Okay, so let's, if the tree is full, we know that half the nodes have a depth of theta log n, which is the height of the tree. The other half of the nodes have a depth sum which is less than the sum at the bottom level alone. This shows that the sum of the depths of all nodes is proportional to log n. Okay. In the worst case, and we talked about the shape of a tree. A shape of a tree is driven not by the keys, but the sequence of the insertions. That's what determines the shape of the tree. We looked at that last time. In the worst case, the BST, the binary search tree, is formed from an ordered sequence. So we get tick, 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 always getting bigger, and just having a big skewness. But we can also have skewness going this way. We can also have skewness going this, and this, and this, and this, and this, and this, zigzagging. So there are many sequences that will give it to us. We're not going to worry about all the sequences. So in the worst case, is formed from an ordered sequence of the smallest or largest is the root. Each number we add is always bigger or smaller value in the BST. In this case, the nodes form a linked list where every node has a right child only. Then the depths of the nodes at the root and going downward, the root is 0. Its right child is 1 because there's only one. Its right grandchild is 2. Great grandchild is 3, 4. They just add up like that. So the average depth is going to be the summation from 0 to n minus 1. As I goes from, summation of I, as I goes from 0 to n minus 1, which of course is going to be theta n squared. So you can see that we have a difference, we have a range of theta log n to theta n squared. So what we need to do is we need to write a recurrence for the sum of the depths of the nodes in an average tree. And so the average tree always becomes a question, what are our assumptions for an average tree? So here is our expression. So our expression, we're going to write d of n, and d is going to represent, c represented comparisons, d is going to represent depths. So the average sum of depths of a tree of height, of a number of nodes equal to n, notice that our expression is recursively or recurrently equal to almost the same expression as we had before. We add d of 0, d of n minus 1, 1 and n minus 2, etc., 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 all the way to d n minus 1, 0, divided by n, which means we're weighing them the same, 1 over n, 1 over n, 1 over n, multiplication, plus n minus 1. And using this summation, we get the depth, and of course this is just a shortcut way of writing all this stuff. So this just gives us a shortcut of doing it. As we go from 0 to n minus 1, we have d of 0, d of 1, d of 2, d of 3, 0, 1, 2, then d of n minus 1, n minus 2, and then finally n minus 1. And this is n minus 1 minus I, so it's going to be d of 0, d of 1, d of 2, etc., all the way to d of n. So does this look familiar? Well, yes, it does. It looks very, very similar. It looks very similar. So let's find out why this works. In equation 5, which is here, in equation 5, let's interpret that. We state that the sum of the depth of the nodes in a binary search tree with n nodes is equal to the average, which is division by n, of its left and right subtrees. So now what we're looking at is, this is going to be the average depth of n nodes in a tree is going to equal to the average depth of a tree which has 0 in the left subtree and n minus 1 in the right subtree, plus the one that has 1 in the left, n minus 2 on the right, 2 on the left, n minus 3, 3, n minus 4, all the way to all the possibilities, and eventually the left subtree gets bigger and the right subtree gets smaller. So these are all the possibilities, and then we'll divide them by n to give them equal probability.
Why did they have n minus 1?
That's what we're going to do. We're going to find out in a second. That's what we're going to find out in a second. Okay. So, so if the tree is an average tree in our definition, then the root is equally likely any of the values. So its subtrees are equally likely to be split 0, n minus 1, etc., etc. You know the trick. Okay. So that's Bhavya wants to know, where does the n minus 1 term come from? Which basically we're using it in our recurrence. That's actually the actual cost. Actual work, actual cost. This is actual cost, right? Could be the work. So di and dn minus I plus 1 are the left and right subtrees of the root. If they are the left and right subtree of, so di means that we have certain number of nodes here, and then we have n minus I plus 1 is going to be the other one. We're going to split them up. So when you add them together, you're going to get what? You're going to add all the n minus 1 nodes of the subtree. So all n minus nodes are, all n minus 1 nodes are one level deeper in the entire tree than the depths of their subtrees. If you think about it, so if I have a subtree here and a subtree here, the sum of the depths of these nodes of this subtree is going to be the sum of the depths. Sum of the depths of this subtree is going to be sum of the depths. But when these become not trees but subtrees, and I add a root to them, what happens to every single depth?
Plus 1.
Okay, if you look at the left subtree, the root of the left subtree has a depth of 0 because it's a root. And every node has a certain depth. The root of the right subtree has a depth of 0, and then it grows by 1 in each level. But once we take these trees and they stop being trees and they become subtrees, then what happens is we get a root on top, and then the left subtree becomes a subtree. So the root of the left subtree, which had a depth of 0, now has a depth of
1.
And the children of the root, which had a depth of 1, have a depth of
2.
So all the nodes increase by
1.
By 1. And how many nodes are there in both subtrees of a tree with n nodes? N minus 1. And that's where we add n minus 1. Does that make sense? So that's the n minus 1. That's the number of comparisons. Okay, so we can see what we do here. So in this case, we're going to solve them very, very similar as we did before. So let me make this just a little bit bigger so we can kind of review that. And so what we have is we have this recurrence. We multiply equation 6 by n, and we get this recurrence, and then we'll simply subtract these from each other like we did before. So this is 7, this is 8 multiplied by n, replicated for n minus 1, and then we're going to subtract. So once we subtract, we're going to subtract, whoops, lost the other part here. So we're going to subtract this minus this is equal to this minus that. And that's what we get. Oops, sorry about that again. And that's what we get here. And again, why do we do that again? To get the... What is it called? Telescope. So we want to have those two summations subtract from each other for a difference, and then cancel all the terms. And then we leave just the extreme terms. That's what a telescope does. So when we do that, you can see that there's a tremendous amount of sameness here. So this is going to go here. This is going to go here, 0 to n minus 2, 0 to n minus 1. So basically only this term stays in when I is equal to n minus 1. Okay? So it's 2 times d of n minus 1. It stays here. And so this whole thing collapses and simplifies. So we have this level here, this resulting here. Notice that now we are solving for d of n, and we still have a little bit of a recurrence, but not much. Okay, so we're going to divide both sides by n times n plus 1, as we did before. And as we multiply by both sides by n times n plus 1, every term gets divided. This one, the n is gone, but when this appears, this one, what happens here? Both of the divisors are going to be here. And this one, what's going to happen? N plus 1 disappears, but n is here. So we'll do this, and then we'll rewrite this. And notice that this equation, right? This equation that we have here, sorry. This equation that we have here can be compared exactly to the same equation you had with quicksort. The comparison quicksort, yep. So at this point, we can see our analysis of the sum of the depths of the nodes is an average BST. Equation 10 is the same as equation 3 in our previous analysis. Okay, so what does that mean? It means that when we solve, we're going to finish the same way, when we solve for d of n, okay, we will find that d of n is equal to 1.38 n LGN. Same. How beautiful is that? Mathematics is very beautiful. Okay, so now, so what is this again? So d of n is equal to 1.38 n LGN. So what is d of n? It's the sum of the depths of what?
Balance.
Of, no.
Probabilities.
Sum of the depths of what kind of BST? Of the average BST. Remember, that's our assumption initially was average, right? The left, right, 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 divided by all the possible ways you can get left, right. That's average. So our average is going to be 1.3. So now, so in that case, if that's the sum of the depths of the average tree, what is the average depth of a node in an average tree? Somebody?
1.38 and
No. That's the sum of the depths of an average tree. What is the average depth of a node in an average BST?
The depth minus 1.
Divided by, divide this result of the sum of all the depths by the number of nodes, which is
And
n. So therefore, when you divide this by n, what do you get?
1.38 log n.
Okay, so we get 1.38 times LGN. So that's the average,
depth of a node.
that's the average depth of a node. And what is the average depth of a node of a full tree, which is the best possible case?
Depth minus 1.
LGN minus 1. So let's think about some number that we can deal with decently. So let's think of a tree that has a million nodes. And a million would be a good number to use, would be 2 to the 20th. That would be a meg. So that's a meg of nodes, right? 2 to the 20th. So what is the average depth of such a tree that has a meg of nodes? Which means that n is equal to, is going to be equal to 2 to the 20th. What's the maximum depth?
20.
I think it's going to be 19. 19. So what is the average depth? 18. Okay, so the average depth is going to be 18. This is BST full, right? And now we're going to look at BST average. This is the average depth. So let's compute this, where n, again, is equal to 2 to the 20th power. So we have that number here, which is going to be 1.38 times LGN. What's LGN?
20.
20. So it's going to be 1.38 times 20. Now, I don't know how much that is, but I do know that 1.38 times 10 is
13.8.
13.8, and then times 2 is going to be 27.6. So what we can see is that if a binary search tree has a million nodes, really a little bit more than a million, a meg nodes, in the best case, our average depth is going to be 20. Why do we care about the average case of the depth of a node? Why do we care about that? Why is that important? Why do we care what the average depth is?
Searching.
Searching. Because the average depth is comparing to what? To the number, the depth is a comparison. Each time you make a comparison, you go deeper, 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 deeper. So if your average depth is very large, you have a very large number of comparisons on average. If you okay, so therefore, in the very best case for a meg of nodes, we have 20 comparisons on average. But if the tree is random and it's not even balanced, which is much, 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 much more likely, then the number of comparisons is 27.6. Is that good or bad? First of all, is it good or is it great? It's really great. Why is it great?
Out of a million, you're only comparing.
Because of the worst case out of a million. Because basically, if it was a skewed tree of any kind of skewness, and if we had the height of the tree approach a million, then the average depth would be 500,000. You're comparing an order of a million to an order of 20. These two are basically essentially the same. They are theta of each other. Because this one basically is this one is LGN minus 2, right? Is that what we decided? And that one is 1.38 LGN. Well, this one is an element of theta log n. But this one also has an element of theta log n. So it shows that the average behavior of a binary search tree is proportional to the best case, which is a very, very lucky thing. Because there's a huge difference in trying to maintain trees and have them be balanced all the time, as opposed to just do nothing. But so let's say we have a tree. So this is a finals question. This is how I'd like you to be able to think. So let's say we have a tree that has 13 million nodes. So you guys have calculators. Let's call it 16 million nodes. I like 16 better. You do too, right? Because 16 is 2 to the 4. So 16 million is going to be 16 million, right? Which is going to be equal to 2 to the 24th. So we know that if this tree was full, then the average height would be what? Would be?
22.
Would be 22. The average height would be 22. And of course, we can compute this one right here. This would be 13.8 times what? And
2.4.
times
2.4.
times 24? 24? So I don't know how much that is, but that's going to be 1.38 times 24. So times 10 would be 13.8. Times 20 would be another 13.8. And 4 times this is going to be 5.2? Rough? I'm just trying to, I don't have a calculator. So 31, 32, 32.2. So 32.2, and in the other case we had what? What's the other one?
22. 1.38 into 22.
This one we had 22, and which one had, so 22, this is 32. So we would expect that on average, the average tree would get 32.2. Okay? Do you believe my analysis? Do you think it's correct? Do you believe this analysis? Does it make sense to you? Of course you believe it. You'd be foolish not to believe it. But now let's say I'm running a tree, and this tree that I have has 16 million nodes. And what I do is I do a traversal of the node, of the tree. You know how to do a traversal of a tree? Some of you do, some of you don't. It's called pre-order, post-order, or in-order traversal. And what I'm going to do is each time I visit a node, I'm going to add its depth to all the previous nodes. I'm going to keep a global depth. And what I'm going to do is I'm going to traverse the 16 million node tree, and I'm going to keep accumulating the depths of this tree. And I expect my answer to be around 32, 33, 34, 31, 30, right? I'll come out of my traversal, I'll have a summation of depths, I'll divide it by 16 million, and the answer I get is going to be 250. I want you to tell me why the 250 is so far away from 32. That's the question. Explain to me what happened, because you're now working for a job and your boss is not happy. Why it's taking so long on average to traverse that tree. What happened? Again? But no, but I should, if the tree is behaving on an average way, I should be able to go through all the nodes, and I should get a very comparable answer to this. But my answer was like 8 times bigger, 8 times worse. So therefore, do you still think that our tree was built according to our model?
No.
No, it's not. Therefore, does that mean that the model is wrong, or does it mean that our assumption for the model were not adhered to? The assumption, the model is still correct, but so which assumptions did we mess up here?
Order of insertion.
Well, not going to go there, but I want to look at this model. You have a good point what you're saying there, but what is not right that happened? What would have to change in this model in order for us to?
They're not all equal.
Okay, so therefore, dividing them by n, which means this is equally likely to happen as this. So what happened was, this assumption that it's equally likely that a node goes left tree or right subtree did not hold. That means our numbers were not, our sequences were skewed some way. We got more things we had sequences of increasing and decreasing that basically create skewness, and of course that created more height, more depth to the tree. So if your result is not following a theta of this, or doesn't look like it's following this because it's so much bigger, that means, what does it mean? It means that the assumptions for the analysis were not being adhered to, which means the data, maybe you had long sequences that were in order, and then you had randomness, and then you had in order. And so things like that. So you had, basically, you didn't have an equal probability of a node going anywhere. Does that make sense? So that's all I'm trying to say here. Okay. So very, very interesting result. I think it's an exciting result because it shows you that if you use a binary tree, you can fully expect it to have a balanced, generally speaking, a balanced profile. It's not going to be balanced, but it's going to behave theta balanced. And that's very, very important.
Professor, can you please repeat how BST full is log n minus 2? I mean, from 20 to 18, however.
I think I had a result in class, maybe you forgot, but basically, if let's say height is equal to 4, all right? So height is equal to 4, meaning you have 1, 2, okay, then you have, this is height is now you get 1, 2, 3, so this is going to be the finish. Okay? So this is what the tree is going to look like. It's going to look like this, like this, like this, like this, like this, like this, like this. That's the tree. Height is equal to 4. So the depth here, so the depth is going to, so again, remember this is going to be the summation. So the depth is 0, 1, 2, 3. Now this tree has n is equal to approximately 16 nodes. It's 15, but I'm going to call it 16. Okay, so let's say 16. So the height is log 2 of 16, which is 4. And therefore our depth, I, is going to go from 0 to LG 16 minus 1. So that's going to be 3. 0, 1, 2, 3. And you've got to multiply I, 2 to the I. So that's how we're going to compute that. I forget what your question was. So repeat your question, please.
How is a BST full tree log n minus 2?
Okay. So I'm not going to show you the whole thing, although it's in one of my notes that I do. Basically, so 50% of the nodes, roughly 50% of the nodes, are at the height of LG n
2 minus 1.
minus 1. So if you actually do the summation of this, and you take the limit as n goes to infinity, they will converge to LGN minus 1, which is going to be 1 less than the worst case. If you think about it, you shouldn't be even surprised. Because, for example, let's say you had 1 million nodes, right? 1 million nodes. Then 500,000 of them are at the worst case, are at log n minus 1. But 1/4 of them are at log n minus 2.
Yes.
So if you just look at those, that's 75% of the nodes. That means that 50% of the nodes are actually worse than I'm telling you the average. The average cannot be any worse than LGN minus 1. It's going to be better than that, because that's the deepest you can go. So therefore, but there's only one node with 1. There's only 2 nodes, 1 node with 0, 2 nodes with 1, 4 nodes with, by the time you get here, you have 500,000 at the depth of LGN minus 2, and then you get 250,000, and then you have 500,000 at LGN minus 1. So I have a solution I can show you in our notes that shows you exactly that this is going to converge to LGN minus 2, which is going to be always 1 better than the maximum depth. This is for full trees. Okay. All right, so let's switch topics completely. I think that's a good idea. And we're going to talk about a different kind of algorithmic hashing. How many are familiar with hashing? 2 people? Okay. So we're going to have to hash you out a little bit. No pun intended there. Actually, it was very easy. Okay, so. Oh, I shouldn't have done that. Huge mistake. Windows cannot handle anything like this. Creativity. Or even small errors, I think. All right, this will be good. Okay. So who can tell me what hashing is in general? What are we trying to do? Who knows about it? Anybody? You know about it, right?
Yeah, from at the end of
Yeah.
advanced stage.
So it's actually just going to be easy for you. Okay, so hashing basically is which part of computer science uses hashing? Data structures or databases, right? So and file structures. So what we have is basically we're trying to find out how we can store something and find it very, very fast. So how do we find things? Well, if you have an array of things or a file of things and they're not in order, you're going to read the first element, you're going to compare it. Did I match it? No. Go to the next one, next one, next one, next one. And we've done this before. It's searching, linear searching, and if things are not in order, you could find it anywhere or not find it at all. So the worst case is theta n. Then we can keep things in order, and if we search for it, it still might be theta n, unless we do binary search, then we could get theta log n. Right? So that's another technique of doing it. So we can do binary searching, we can do linear searching. Okay. Hashing says, don't search for it at all. Just figure out a magic number and go there. That's kind of what it says. So the linear search is big O of n, theta n. Binary search is log n. Okay. Now we can also have something called hierarchical index search. And that's basically having an index which has multiple levels. We didn't really talk about this in the class, so don't worry about it. But hashing is a way to locate the data as a function of the data itself rather than any comparisons at all. So we're not going to be comparing to see whether something is not matching. We're just going to find out where it is and say, is it a match? If it is, we succeed. If it's not there. Okay, so the ideal complexity is big O of 1, which means we do a series of constant operations. We go to our location, and we find it, or we fail to find it. That's the ideal. It doesn't always work that way. Okay, so let's take a look at how hashing works. Let's say we wanted to store 25 keys in the range from 0 to 999. 999. So how many different keys are there? 1,000 keys. So what I could do is, since I have 25 keys, I'm going to store them in a hash table. Think of a hash table as a big array of storage, or think of it as a file, where we just write one number after another. So either an array or a file. In any way, it's a linear structure. Each hash table entry for finding has a key and a reference. Key is the key that you're searching for, and reference is where to find it. Okay? So we'll take a table or hash table of 1,000 elements, put a -1 for all the keys, and we're going to store each key value of I at hash table sub I. So if the key is 235, it's going to go into location 235. That way, if I go to hash table 235, if it's empty, it's not there. If it's full, it's there. So I don't have to compare any bus to anybody else. I just see if it has to be there. So 25 of the 1,000 hash table records are valid. All the other ones are -1s because there's nothing there, because I only have 25 keys. So only 25 locations of these 1,000 locations are filled. So that means 975 are what? Empty. Which is fine, except that it means that 975 out of 1,000, that's 97.5% of the storage is wasted. But we're rich, so we can afford it. So we're going to say, okay, that's fine. Okay, so our hash function, if you want to search for hash table, hash function for key I is just go to index I in the hash table. Very simple. All right, and to check if the hash table 120 has 123, just compute H123. It says, okay, go look at location 123, and we go there. Okay, so in that case, check this one, compare against the key field. If it matches, then we are successful. So if the compare matches, we're correct. If it's a -1, then nothing gets stored there. Okay, so you can see sort of what it would look like. So here's an example of a hash table. Now here, notice that this is location 1, 2, 3, 123. What's -1 mean? It's empty, nothing is there. And this is a reference. So let's see how else we can do this. So our hashing function H satisfies the big O of 1 requirement for immediate lookup. The hash table implementation is not efficient because we have this lack of usage. If we had a set of employees, let's say 500 of them, each one has a social security number, we could make the key for the hash table the social security number. How many digits is the social security?
1, 2, 3, 4, 5, 6, 7, 8, 9.
Has 9. Okay, that's the answer. So the hash table would need base 10 to the 9th location. That's 1 billion locations. So all I would need to do is have 1 billion locations, but I'm only going to use how many of them? 500. So now I'm really wasting space. So this is kind of a bad idea, right? So basically the wasted space would be this number over 1 billion, which is my inefficiency of space would be 0.999999995. Okay, that's like wanting to drive a car. So you buy all the Ford Mustangs in the world and you just drive one. It's nice, but it's not efficient. You're wasting a lot of resources, right? All right. So basically, to improve this approach, we cannot waste that much memory because it's just ridiculous. So what we could do is basically, in the example of 25 unique keys in this range, we could create a hash table only with 25 locations. And now, since it's only 25 locations, we cannot have the hash function just be I. But we could have the hash function be h of I equals I modulo 25, because that would return an index from 0 to 24. So I could take the key value, divide it by 25, look at the remainder. Look at the remainder. The remainder would give us 0 to 24, which gives us 25 possible locations, and that's good, because now I'm wasting 0 in terms of space. So example of the hash table would be if we're hashing, let's say the number 52, if you do 52 modulo 25, that's going to be 2. So 52 is going to be going to here. So 52 goes into location 2, 0, 1, 2. How come 500 goes into 0? How come key 500 goes into 0? 500 modulo 25 is 0. Okay. How come H49 is 24? Okay, because if I take a remainder, if I divide 49 by 25, it goes in ones of a remainder of 24, so it's going to go to location 24. So 0, 1, 2, 3, down to 24.
If I have h of 1000, one more number,
Yes.
h of 1000,
Yes.
example, then that modulo will also be
0. Okay, so now you're ahead of me. That's good. I like it when you're ahead of me. So yes, so right. Kabavia is very right, because what I'm showing you about different keys and they're going to different locations. But it's also possible that you might, it depends on your keys, you might have the same location. For example, what is another number bigger than 49 that also gets 24?
50. 50.
What is it, 99?
24.
24? What's it bigger than 49?
50.
What's the smallest number bigger than 49 that goes to 24? 70? 70? 74. Because if you divide 74 by 25, you're going to get 2, the remainder of 24. Okay, so that's what I'm talking about. So here I'm showing you exactly that issue, that problem, is that if somebody's got an ID or a key of 273 and 73, they will both go to 73, to 23 rather, which is, that's a problem, because if you're going to put them in the same spot, that means they're going to basically try to go in the same location, and that's called a collision. It's called a collision. So, in fact, if we look at the formula 25 times I plus 23, any number where I is 0, 1, 2, 3, all the way up to 39, okay, plus 23 is going to be having a modulo equal to 23. So it's possible that we have a whole number of keys. This is showing you 40 keys could all want to hash to one location. So that's a problem, right? So in general, we will have 1,000 divided by 25 key values, which will return the same location. So we have a lot of potential for collisions. How many collisions are we going to get? I don't know, but potential for collisions. So since we do not know in general what the keys look like, because the keys may be coming in real time, we have a real chance of two keys colliding. In the hashing function, we need to be able to handle collisions. Okay, how do we do that? One approach is called linear probing. Linear probing is very straightforward. What happens is, so let's say this is my storage here, and I have a key, and the key says hash here, so it goes here. Then I have a different key, and the hash function says go to the same place. Now we have a collision. So in that case, we say, okay, I can't go here because the value here is not -1. That means something's already in there. How about the next location? Oh, that's available. So linear probing, we go one by one to find the next available location, and we try to store it that way. It's called linear probing. And that explains it right there. Very, very simple. So once we don't find what we're looking for because somebody else... Now, what happens if we search for something and the key value at that location we're searching is -1? What does it mean?
empty.
It's empty. What if we search for a key of 25 and we find out that the key in there is 75? Where are we going to search? Now we're going to do linear probing. Because somebody else went. Now, it doesn't mean that we're there. We might not be there. Think about this. So let's say we have a table here, hash table. So here's some locations. So let's say this is location I, and I have a key here. Let's say the key is 37. Let's say this key is 45. This is -1. This is 66. This is 3. Okay. And let's say I'm looking for a 37. So I do a hash of 37. What's that function going to return? It's better, right? So it should return I hope. And if I go there, I go to the ith location and I compare. Does this equal this? And the answer is yes. So that's a match. But let's say I'm searching for 126. And let's say for some reason that also returns I. So I compare and I say, is this a match?
No.
No. Not a match. So I do linear probing. Is this a match?
No.
Oh. How about this one?
No.
Should I continue? Why not?
Because it should be there if it is.
It should be there, but it's empty. Now, it's not so simple. It's possible that 126 is here. You say, well, how could it be here? Well, maybe there was another value that was here, like 32, and then when we erased it, we put a -1 in here. So if this 32 was here, maybe a better thing to do is we can mark it with a special character. And that means it's empty. It's just like a -1. It's empty, but something was there before. In hash table technology, this is called a tombstone. You know what a tombstone is? Does that word sound familiar to you, tombstone?
Great.
You know what a cemetery is? Where dead people are living, live people are dying, I don't know. That's a little joke. That's a little joke. So in a cemetery, we have the person is in the ground, and then we have a tombstone. What is a tombstone for? That tells us who's here. We don't see them, but we know they were there. They were there in the world. So a tombstone is a special marker that says something was there. It's not there anymore. So therefore, for looking for 126, no tombstone, which means it's either not there. It does mean 126, we're going to find 126, but it means don't stop looking. Now we find it. Now what happens if we have a -1 here?
Then we stop. If there is no tombstone there.
Now
Stop.
we can stop. Because if that means 126, what does it mean 126? Was it ever there?
No.
Maybe. Could have been here. Could have been here? Not a tombstone. Could have been here. Maybe 126, maybe not. But definitely no longer there by this point.
So what is the use of hash table again? We are comparing again, and it's an overhead, but that you have a marking that tombstone, and we are comparing again.
I'm not sure.
That's the same strategy that we are comparing in a linear search again. Why we are using
Yes.
hash table? We are comparing here as well.
Why are you always one step ahead of me? Good. That's right. So we may have better techniques. Better techniques. And also, this technique it's simple, right? But maybe it's not the best. So how can we improve hashing? So I'll come back to that answer. We can increase the table. First of all, interesting thing that we're going to find is, let's say we create a perfect hashing function. Now I want to make one thing very, very clear. Perfect hashing is a special terminology. Perfect hashing is like I have 10 keys, their numbers is 0 through 9, and I create an array of 10 elements, and I put each one into its correct index. That's perfect hashing. You will never have a collision. But if you have 10,000 people in a large corporation, they have social security numbers, you cannot create 1 billion locations and store 1,000 people or 10,000 people, because then you're wasting almost the whole table, right? So therefore, in that case, what are you going to do? So you don't want to have the table be too big. You want the table as small as possible. The question is, how small do we want it? The minimum the table can be is equal to the number of keys. Okay? But if we use, so if we have 100 keys, the hash table could be 100. 10,000 keys, it could be 10,000. However, here's what happens. So let me explain to you the optimal hashing function. This is a probability definition. The optimal hashing function is a hashing function where every location in the hash table, 10,000, 20,000, 50,000, 500, where every location in the hash table has an equal probability of being selected by the hashing function. Okay? Does that make sense? Every key in the hashing table has an equally likely chance of being selected. That's the best we can do. But it turns out that if the number of keys and the number of locations that I'm going to call slots, locations or slots in the hash table are equal, even the best hashing function is going to create a tremendous amount of collisions, and it's also going to never target a large number like 37% of the slots in the hash table. Meaning that if I have 1,000 records and 1,000 slots in the best hashing function possible, not perfect hashing, because that means we'd have to have 10,000 and our keys have to be from 0 to 9999. But social security numbers, and we have 1,000 of them, let's say we have 1,000 of them, and we have 1,000 locations and 1,000 social security numbers. 367 of those locations, on average, will never be targeted by the hashing function, even if you make the best hashing function. That should be shocking. That is a little bit shocking. Yeah, comment?
Why? I mean, why?
Why? Well, I'm not going to argue and tell you why, but I will show you mathematically why. Okay? There's a very good mathematical basis for that, for the answer to this. So, since making the table exactly the size of the number of records, making the slots and the records the same, it means we're going to get a lot of collisions in the best case and a whole lot of collisions in worst cases. So it's going to be a disaster. So the question becomes, I mean, think about it this way. Think about, and this is a crazy different, but think about, let's say you have, you guys ever play darts? You know, you throw the darts like that? So instead of darts, we're going to make a hash table. And the hash table is going to have 100 slots. And you're going to stand far away, and you're going to throw, and you're going to throw, and you're going to throw. And hopefully, let's say you're trying to hit any one of the places. You're going to be off a lot. You're going to, and when you throw 100 darts and there's 100 slots, there's going to be a lot of slots that you miss. There's going to be a lot of slots that get hit twice. There's going to be a few darts that don't hit anything, but you can throw those over again. Because we want everything to land. So that's going to be a problem. So our solution is this. Because having the same number of slots and records creates all these collisions, we're going to do something about it. The number of records cannot be changed. We need to store our records, we need our records. But it doesn't mean that we have to have our slots. We can make, for example, 2R slots, double. What's going to happen to that? Well, what happens is if you double the number of slots, what's going to happen is the probability of a collision, with everything being equally likely, the probability of a collision is going to go down because there's more room, there's more dispersion across the hash table. Does that make sense? If I create a hash table which is twice as big as the number of records, and each of those locations is equally likely to get targeted, then I have much more room for targeting. So therefore what's going to happen is the number of collisions are going to be reduced. And again, we'll show this mathematically, but this is absolutely true. So, increased table capacity is what we just did. Or we can resolve collisions in a different way. Maybe have a different technique for collisions, or maybe use a different hashing function. Okay. So these are some ideas. One of the things that we're going to talk about, an important terminology, is called packing density. Packing density, very, very simple idea. The percentage of the hash table which is used to store the data records. The percentage of the table used to store the data records. So for example, if I have R slots and I have R records, then every single slot is full. Because every record will go to some slot. So therefore my packing density is 100%. But if I have 100 records and I make 200 slots, then my packing density goes to 50%. Okay? Question. If I have a hashing table with a packing density of 50% and the amount of data is 100, how big is the hashing table?
200.
200. If I have 100 records and my packing density is 60%, what's the size of my table?
60.
Yeah, so I have 100 records and my packing density is 60%. How big is the hashing table? It's going to be 100 divided by 0.6, which is 100 divided by 6 over 10, which is 100 divided by 3 over 5, which is 100 times 5/3, which is 100 plus 2/3 of 100. Number of slots? 167 roughly, right? 1.1 2/3 times 100, 167. I have 100 records. My packing density is 70%. How big is my table? Multiply it by 10 over 7. Divided by 7 tenths by 10 over 7. 10 over 7 is 7 over 7 and 3/7. That's going to be 100. What's 1/7 of 100? Around 14. So 30% is going to be 42. So about 142. You got a calculator? I think you're going to use it. Because I don't think you guys can do what I do. I don't know how I do it, but don't worry about it. I can't tell you my secret. All right. And even if I did, you wouldn't want to use it. All right. Anyway, so you understand packing density. Okay, so finish the sentence. The lower the packing density, the what likelihood of a collision? The lower the packing density, the what likelihood of a collision?
Less collisions.
The lower the probability of a collision. The bigger the packing density,
Higher.
the higher. So if we have, so what's the highest probability of a collision? Where the number of slots in the hash table is equal to the number of records. When the packing density is 100, that's the worst case. Is it possible that we have 50 records and 50 slots and our hashing function magically gives us no collisions? Is it possible? The answer is yes, but it is highly unlikely. I can show you how likely it is, and it's not very likely. Because even the best hashing, and again, this is excluding perfect hashing. Perfect hashing, that's kind of like cheating. Not really. It's not cheating. It's only for special cases. Never for general cases. Cannot use it. Okay. Another way of handling collisions is called chaining. Chaining is a very simple approach. So chaining looks like this. You still have a hashing function. But the hash table is, so normally the hashing table has a key and then might have an index or a location where the record is found. But in the case here, let's say we have 37 hashes to I. So what happens is you create a linked list or a chain with 37. Does that make sense? And then if 126 also hashes to I, then we basically go here, we see that 37 is already in the chain, but 37 is different from 126, and that's the end of the list. So we're going to put a 126 here and close the chain. Get the idea? This is called chaining. So now with chaining, we can't exactly talk as the number of, we can't really talk about packing density. Because now we can talk about the number of chains. If I have 100 records and 100 chains, is that a problem? Now it's a smaller problem. Are we going to get collisions?
No.
Okay, let me ask you a question. Think about your answer. Suppose I have 100 slots. I have 100, not slots, I have 100 chains. Chains. 100 chains, I have 100 records. I have the best possible hashing function, not perfect hashing, just the best possible normal hashing function. How many of these 100 chains are going to have a length of 0? Anybody? I know you don't really know, but I told you what to expect before. It's the same number. Roughly speaking, 37% of the chains will have 0 records go to them, which means that there will be other chains that have 2, 3, maybe even 4. Will there be a chain with a great hashing function? Will there be a chain of 100?
Yes.
No.
I mean, if
That will be the hashing function which says hashing function of any key is always the same index.
Yeah.
That can happen,
That's
but
the
that's a
worst
horrible. That's called the worst possible hashing
The worst
function. I'm saying we have the best possible hashing function that we can have. So even the best possible hashing function is going to leave 37% of the chains empty, and it's going to make few chains have a length of 2, 3, 4, maybe 5. It's unlikely they're going to be 10 or 20 or 30, because then it's like, okay, is this really the best possible hashing function? I don't believe it. Okay, so we don't believe that. Okay, so chaining is very, very interesting. We'll do some analysis of chaining. Another way of handling collisions is something called quadratic probing, just like linear probing. But basically, once you have a collision, this is no chaining anymore. But once you have a collision, you go 1 squared minus 1 squared plus 2 squared 2 squared. 3 squared, 9 up, 9 down. So basically, instead of trying to pile everything around the collision, you try to go quadratically far away from the collision so you don't create clumps. Is it better? Maybe. It's different. Quadratic. All right, let's see how much time we have so I can finish this little chaining analysis here. I have a feeling I'm running short on time. It's always right.
It's time.
Oh, is it time? Yeah. It is time. Okay. Goodbye. I'm going to stop here. Well, let me just. Camera guys, you still here? So give me 3 minutes. Okay, then we'll finish this one. So the idea is, so now we're going to look at the whole idea of chaining. So the basic average analysis of hashing implemented with chaining. We're going to assume a hash table has m locations. That means there are m chains. And we're going to assume n entries. Now, of course, it's possible for m and n to be the same. Because chaining doesn't have a problem with collisions. It just kind of creates these lists. But if it's a good hashing algorithm, the lists are going to be relatively short, we hope, right? And if the list only has 2 or 3 records in it, that's almost like theta 1, right? We don't want them to have n records in it. That would be bad. So we're going to assume that every list has the probability of 1 over m. Where we have m lists, each list has the probability of 1 over m, likelihood of being chosen by the hashing function. So if we have 100 chains, each one has the probability of 1 over 100. And these are the chains. Chain 0, chain 1, chain 2, all the way to chain m minus 1. And then we have the length of list 0. So after everything has been hashed, we have a certain number of records here. Chain, 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 chain. And so we have the length of every list. If we add up all these lists, what's the sum of all these? What's the sum of all the lengths of the lists? Ronaldo, you're so quiet. Well, we're gonna add up all the m lists, the lengths of them, and that's going to add up to what? It's going to have all the records. And how many records do we have? N. So yeah, so I don't know how much these are, but I know they sum to n. I do know that. Okay, so now what I'm going to have the average complexity of an insertion at the back of the list. So now assume that I'm going to, so that's the idea here. I'm going to insert something. Now the lists already have some records in them. I'm going to put a new key, and the key is going to say go here. So if I go here, I'm going to have to make sure that it's not already in there. It's not already in there. And if that's the last one, it doesn't match, add it. But if it's already in there, don't add it, because we don't want to have duplicates. So let's look at the average complexity of insertion at the back of the list. We have to go to the back of the list because we have to make sure we don't have a duplicate. So the average complexity, this is our average analysis, is going to be the sum from 0, tick, 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 to m minus 1, the probability of selecting that one times ti of n, which is the amount of work to do the insertion. Now, the probability is 1 over m, so that comes out in front of the summation. And the summation here goes from 0 to m minus 1, the length of the list. Now, I don't know how much any of the lists are, but I know if I sum all the lists, I will get m. So what I get is 1 over m times n, which is n over m. That's the expected what? Cost of inserting at the back of a list. So therefore, because the sum of all lists must equal, therefore if m is about the same value as n, we have an average cost is about big O of 1. That's our analysis, and we'll continue with that next time.